Hello, I just wanted to talk to you about section 3.6, and this is what we've been alluding to a lot in class lately, where we're going to graph functions that we're given. So it's called a summary of curve sketching. So we're not going to plot points like maybe we would have when we first started learning graphing, a long time ago. But we're just going to focus on the key parts of the function. And so that's why we would call it sketching, because we might not get it exactly right, but we're going to have a very good idea of what's going on based on a list of things that we'll be searching for. And again, as I've mentioned, this is going to pull together everything that we have been working on in the last, while, just all the parts about derivatives that we learned about, and even stuff that was back in that chapter P that was a review. So x and y intercepts, how can we find where it crosses the x-axis? How can we find where it crosses the y-axis? Again, that should be mostly familiar to you. The one that I want to talk about for just a second is symmetry, because while we did that in chapter P, we haven't really looked at it a whole bunch since then. So just a note, if you're going back to look for it, this comes on page 5 of the textbook. And I just want to point out what those three different types of symmetry are. So the first is symmetry with respect to, I'm just going to write WRT, with respect to the y-axis. And again, that our famous one is the parabola, like that. And so what we said was that if we find f of negative x, it is the same as f of x. All right, that plugging in a negative x does nothing. It gives us right back to the original function. The other word we had for this, so I'm going to write also known as an even function. All right, the second type of symmetry was symmetry with respect to the x-axis. And for this one, we said if xy is on the graph, then negative x, negative y is also on the graph, or is too. But this is not a function. Again, if we have symmetry with respect to the x-axis, we're talking about something like this, and that's not a function. And we will not be graphing anything that's not a function. Everything that we will be graphing is a function. And so while this is a symmetry, we're not going to look at that type. We just won't run into it. And then the final type is symmetry with respect to the origin. And in that case, we found that f of negative x was equal to negative f of x. Again, the celebrity of this type is the one. It's like a cubic, where if I put in 1 and get 1, right, then when I put in negative 1, I get negative 1. So again, if I plug in negative x, all right, so again, for example here, negative 1, I get the opposite of what I got when I plugged in positive 1. So for positive 1, I got positive 1. When I plug in the opposite of positive 1, I get out the opposite of what I did here. All right, and this is also known as odd functions. All right, then domain and range. We'll talk about continuity. Where is it going to be continuous? Where is it not going to be continuous? Where are the vertical asymptotes? Where is it differentiable? Again, we're looking for things like sharp turns, or where there is a vertical tangent line, relative extrema. Again, that came in chapter 3 at our very first section. Concavity, we've just finished talking about that. Points of inflection, horizontal asymptotes, infinite limits at infinity. So again, all things, these last 4 right here are things that we've been talking about very, very recently. Okay, so for how do we analyze a function to figure out what its graph is going to look like? So first, determine the domain and the range of the function. Really, a big part here is going to be the domain. The range, it might not be as obvious until we actually graph it. So for this part, we definitely want to know what the domain is. What am I allowed to plug in for x? What am I not allowed to plug in for x? Find any x-intercepts, y-intercepts, where are their vertical asymptotes, where are their horizontal asymptotes. Find the symmetry of the graph. That's just going to help us get a better idea. If it is symmetric, we'll know, hey, if I graph on this side of the x-axis, or I'm sorry, the y-axis, then it's going to be exactly the same on the opposite side. Or that if I graph in the first quadrant, then I can say that I can graph the same in the third quadrant. All right, that's not going to get us any points per se, but it just will help us to get a better idea of what the graph is going to look like. Locate the x values for which f prime of x and f double prime of x either are 0 or do not exist. Again, these are going to be our critical numbers and our possible points of inflection. Use the results to determine relative extrema and points of inflection. Okay, so let's do one here. Analyze and sketch the graph of f of x equals 2 times the quantity x squared minus 9 over x squared minus 4. And when I made this sheet, I put things in the order in which they did them in the textbook, and I'm kind of regretting that now, because one thing I would like us to talk about first, and we'll get to this on the next page, but is what is the domain? Only because when we're looking for critical numbers, when we're looking for possible points of inflection, we want to make sure we don't include anything in that list that's not actually a critical number or a point of inflection. So let's just look here. Where is this going to be undefined? All right, that would be what the domain is. So think about that for just a second. All right, hopefully you just said there, x cannot be equal to -2 and it cannot be equal to +2. Right, again, if we were to write that formally, we would say it's everything from -infinity to -2, together with everything from -2 to +2, and then from 2 to infinity. We just cannot include positive and -2. I'm fine with you writing that. So that means that if we happen to get a critical number that is 2 or -2, we realize, oh wait, it's not actually a critical number because it wasn't in the domain to begin with. If we should happen to get it for a potential point of inflection, we don't want to include that, all right, as a possible point of inflection. It will go in our table because something interesting happens there. We'll have a vertical asymptote, and it could change from increasing to decreasing. It could change concavity there, but we can't count it as a critical number or a point of inflection. Okay, let's take the first derivative. I'm going to suggest that you pause for just a second because you know how to do this. You don't have to watch me do it. So pause and go ahead and do that, and then come back and just check to make sure that you got the same thing I did. All right, so first derivative, we're going to use the quotient rule. So that is bottom times the derivative of the top. So that is going to be this constant or coefficient of 2, and then we're going to end up with a 2x in there for the derivative of that, minus, all right, so bottom times the derivative of the top minus the top times the derivative of the bottom, which is 2x all over the bottom squared. And then when I simplify that, I'm going to end up with, let me pull out a 4x from each of them because they both have that right here. So then we end up with 4x times x squared minus 4 minus x squared minus 9. Oops, I forgot to square this. All over x squared minus 4 squared. When I combine like terms here, these x squareds are going to cancel out, so we'll just have -4 minus a -9, which ends up giving us a 5. All right, so our final cleaned up version of this is the 5 here times the 4 here gives us 20x over x squared minus 4 squared. All right, again, you could say, I don't feel like cleaning that up, but it's going to be much more difficult now to take the second derivative of that, so it's good that we've done that. Okay, again, second derivative, we're going to use the quotient rule, so go ahead and do that. So pause the video and see what you get. Okay, second derivative, just so you can check your work here, bottom times the derivative of the top minus the top times the derivative of the bottom here. This is going to be chain rule. All right, so we're going to have a 2 coming down in the front times the x squared minus 4, decrease the power by 1, so it goes from a 2 to a 1, and then we've got the derivative of the inside, which is 2x. Sorry, this is getting very tight. All over the bottom squared, which is going to be x squared minus 4 squared. Okay, let me clean up the top here. Again, we're going to need to find the potential points of inflection, and so we're definitely going to need this in a much neater form. All right, so I noticed that they both have an x squared minus 4, just one of them. This has an extra one, but they both have one. And both of them have a 20. And that is it for right now. Maybe when we simplify, we'll see more things. So let me come back over here. So f double prime of x, I'm going to take out the 20, x squared minus 4. And then what's left here is 1 x squared minus 4. This is gone, this is gone, this is gone. So all that's left is 2 times 2 is 4, and x times x is x squared. So we end up with 4x squared all over x squared minus 4 to the 4th. Whoops, I keep forgetting to square the denominator. Sorry about that. Okay. So then this simplifies into, well, one of these, this one will cancel out with one of these, so we'll just end up with x squared minus 4 to the 3rd. And then x squared minus 4x squared, we're going to end up with 20 times negative 3x squared minus 4 over x squared minus 4 to the 4th. All right, so that is our second derivative. And here is our first. As we get to the next page, I'm going to transfer them over there so we don't have to keep flipping back and forth, but for right now, we'll just stay with that. All right, x-intercepts. How do we find the x-intercepts? All right, so hopefully you're saying, oh, x-intercepts are where we have a value for the x, not necessarily 0, but the y is definitely 0. And so what we need to do is we need to say, when is... again, this is so smushy, I'm sorry. When is the function equal to 0? So we've got 2 times x squared minus 9 over x squared minus 4. When is that equal to 0? Well, we could just cross multiply right here, and we would end up with 0 equals 2 times x squared minus 9. We also talked about this in class very recently, that when we have a rational function, that the x-intercepts come by setting the numerator equal to 0. That's because if we cross multiply, the denominator gets wiped out by that. So we would just say here, it's when is 2 times x squared minus 9 equal to 0. Again, you could divide both sides by 0, so that would just give when is x squared equal to 9, and that would be x equals plus or minus 3. Again, notice I'm not saying where is the denominator 0, because it's the same denominator that we had here, and we already eliminated the numbers that cause this to be 0 because they're not in the domain. So again, in other situations, if we have a fractional exponent less than 1, we would definitely need to look at the denominator because it probably wasn't there before we took the derivative. But here, we're just going to say, no, there are no, oh wait, I have no idea what I'm talking about right there. Sorry, totally making that up. That's for the critical numbers, and we have not talked about that yet. Sorry. Come back to that in just a second. So right now I'm just looking for where is the numerator 0. Okay, for the y-intercept, that is what happens when we plug 0 in for x. All right, so in this case, f of x or y is equal to 2 times 0 squared minus 9 over 0 squared minus 4. And this gives me negative 18 over negative 4. And then this gives me 9/2. All right, we might have multiple x-intercepts, but we'll only have one y-intercept. Okay, vertical asymptotes. All right, where will those occur? All right, hopefully you said at 2 and negative 2. Again, that comes from setting the denominator equal to 0. We already did that with the domain. So we would have x equals 2 and x equals negative 2 as the vertical asymptotes. All right, horizontal asymptotes. Again, this was something that we just discussed recently. This is where we compare in a rational function, we compare the term of highest degree in numerator and denominator. And here the powers are equal. All right, and so then we just say, well, then it's just the ratio of the leading coefficient. So here the leading coefficient would be 2 if we distributed that through, and here it would be 1. So the horizontal asymptote will be at y equals 2. Again, it's horizontal, and therefore it's hitting the y-axis. That's why it gets a y equals 2. Here are vertical asymptotes. They go like this, and they hit the x-axis, which is why they're called x equals negative 2, x equals 2. Okay, let's go to the next side and or to the next page. And as I do that, I'm going to rewrite what the first and the second derivative are. So here are f prime of x. Again, this is just so we don't have to keep flipping back and forth, is 20x over x squared minus 4 squared. And our f double prime of x is equal to 20 times negative 3x squared minus 4 all over x squared minus 4 to the 4th. I'm going to do one thing with this, and that is I'm going to factor out the negative in here. So we'll write this as negative 20 times 3x squared plus 4 over x squared minus 4 to the 4th. The only reason I'm doing that is because this is always going to be positive, this is always going to be negative, and so we know that the numerator is always going to be negative. When we're testing values in there, that could be helpful to us. It might not be as obvious here, so I'm just hoping to make it more explicit. Okay, so then let's talk about critical numbers. Right? Again, critical numbers come from where is the first derivative equal to 0, or where is it undefined. But again, specifically, where is it undefined where it was originally not undefined? So within its domain, where is it undefined? And again, we already said we're not going to have any values like that because we've already said 2 and negative 2 are not in our domain. So anything we get down here from setting the denominator equal to 0 is not a critical number. It's important, but it's not a critical number. All right, so the only ones we're going to get are by setting the numerator equal to 0. Right, so where is 20x equal to 0? And that just occurs at x equals 0. All right, so our critical number is x equals 0. All right, possible points of inflection. That comes from setting the second derivative equal to 0 or finding out where the second derivative is undefined. Again, we're not going to get any about the undefined part because we've already eliminated 2 and negative 2. So we're just looking at where is the numerator equal to 0. All right, so we're going to say negative 20 times 3x squared plus 4. When is that equal to 0? Again, I could divide both sides by negative 20. So really what I'm looking for is where is 3x squared plus 4 equal to 0? And hopefully you realize nowhere. If I subtract 4 from both sides, then I end up with 3x squared equals negative 4. And I cannot possibly square a number, multiply it by a positive, and get a negative. So possible points of inflection, none. All right, this is why I'm apologizing, because I waited until the very end here to write domain, and we might have already made bad conclusions about 2 and negative 2 if we hadn't looked at that first. So the domain, as we wrote before, is negative infinity to negative 2, together with negative 2 to 2, together with 2 to infinity. All right, let's check for symmetry. So in each case when we check for symmetry, we have to find out what f of negative x is. We want to see, is it exactly the same as f of x, or is it the exact opposite of f of x? Because if one of those two happens, it does have symmetry. So let's plug negative x into our original. And again, this is 2 times negative x squared minus 9 over negative x squared minus 4. All right, when we simplify that out, we end up with 2 times x squared minus 9 over x squared minus 4. So yes, this is symmetric. It's an even function. In other words, it has y-axis symmetry. So y-axis symmetry, or we could say it's even. And again, that's just going to help as we sketch our graph. Okay, now let's make our table. Now, if you remember before when we did this, we had all our intervals at the top like this, and then we had our what it was that it was deciding for us over here. But we're going to reverse it now because we've got so much information right here. All right, so we have to find out what our test intervals are. Our test intervals are going to come from our vertical asymptotes. They're going to come from our critical numbers, and they're going to come from our possible points of inflection. All right, so I'm just going to list all of those, and then we'll write them in an order here so that we can make our table right here. So vertical asymptotes, there are two. They're at -2 and +2. Our critical numbers, the only critical number we had was x equals 0. And we had no possible points of inflection. Okay, so then what we're going to do as we fill this in is we're first going to say what, let me just put these in order. So if I were to write this on a number line, it's -2 to 0 to 2. All right, those are the only three values that we have in here. So we're going to first say this whole interval right here. So -∞ to -2. And then we have to stop and test x equals -2 because it is, I'm sorry, no, we don't have to do that. We'll just say x equals -2. If it were like here, we'll have to test it, but here we're just going to acknowledge that it's a vertical asymptote. Then we say the next interval, so -2 to 2. And then we say, nope, my goodness, -2 to 0. And then we say what's going on at 0. And then we say 0 to 2, and we say what's going on at 2, and then 2 to infinity. All right, so again, all these values that we found that were important as stopping points, we're making sure that they have their own separate line, but then it's the interval leading up to that, the interval between that one and the next one. Sorry, you might not even be able to see that. Interval between that one and the next, test that one, interval between that and the next, and then test that, and then do the final interval right here. Before we do that, I'm going to write in the little margin here why they ended up on our table. So I'm going to write here that -2 ended up in here because it's a vertical asymptote. Same thing here as +2. And this right here is because it's a critical number. That just means for here, we're not going to really find anything. We're just going to say that it's a vertical asymptote. We'll say the same thing here. Right, but here, this could be a relative extrema. It could be a max, it could be a min. We might find out it's a nothing, all right? Maybe it does one of these things that we've seen before where it has a horizontal tangent line, but it's not a max or a min. But I like to have that in there so that when I get to that point and I forget why it ended up in the table and what my analysis is saying, I remember, oh yeah, this is probably going to be a max or a min. Okay, let's do this. So for all the intervals in f of x, we're just going to cross them out. I can't tell about anything on an interval of the original function. So every time you have an interval here, just in f of x, let's cross it out. All right, I'm not doing anything there. And then in each of these values under f of x, I'm trying to find out what the coordinate is because I'm going to have to plot this point right here. All right, and again, at -2, it's undefined, so we would just say it's undefined. All right, f of 0, again, I probably should have written what f of x is here. It was 2 times x squared minus 9 over x squared minus 4. And we just happen to find what the value of this is because it is the it's the y-intercept, and so we found that this was 9/2. And then at 2, we're going to say, again, it's undefined. Okay, f prime. Now we are going to test everything. We're going to test the interval. We're going to say what's going on at that point. We're going to test this interval, say what's going on at that point. So we'll just have a bunch of positives and negatives here. All right, so this column is not the actual value of the function. It's just we want to know whether it's positive or negative because this is going to tell us about increasing and decreasing. All right, so I need to pick a test point in here. I'm going to pick -3, and I'm just going to write a little note to myself, again, because I forget, and then I test a different point or something. So I'm just going to test -3 here. So in the first derivative, and again, you'll be able to look at yours. I'm going to have to scooch my paper down. But I'm going to plug -3 in here. So 20 times -3 is negative. And then when I plug -3 in here, actually, it doesn't even matter because whatever I get, it's squared, so it's always going to be positive. So denominator here will always be positive. So then I've got 20 times -3 over something positive. That means that in this interval, it's negative. All right, if I plug -2 in here, we already know it's going to be undefined. So we're going to write that. All right, I'm going to pick a test point in here. Between -2 and 0, I'm going to pick -1 as my test point. I go back up to the derivative. If I plug -1 in here, again, it's negative in the top. This is always going to be positive, or 0, but those we have on here already as the vertical asymptote. So in this case, it's negative. All right, when we plug 0 into the derivative, we get 20 times 0 is 0. Again, this is going to be positive, so we get 0. Well, that shouldn't be a surprise because that's how it ended up on our list. It was a critical number where the derivative of f is equal to 0. All right, in 0 to 2, I'm going to pick the point 1. So I go up here, 20 times 1 is positive over positive. Vertical asymptote, the derivative is going to be undefined. And then in this one, I'll pick 3. Actually, this is where the symmetry helps us. Not so much. That would help us in here, and it's going to help us in the graph. All right, we put in 3. 20 times 3 is positive. This is going to be positive. All right, we do the same thing for the second derivative. All right, now we're looking at this. Again, this is always negative. This is always positive, so our numerator is always going to be negative. We're also going to, let's see, I just want to make sure that I am correct in here because I do have it changing from positive to negative. What did I do? Yeah, interesting. Okay. So when I put in -3 in here, -3 is going to make this negative. Well, it's going to be positive, this is going to be negative, so it's going to be negative. This is undefined. Sorry, I can't tell if you can see. At -1, again, that should be negative, but I have positive. Oh, I know why. Devil. Okay. It's because this is a 3. I forgot that that was a 3. All right, sorry. Hopefully you weren't worrying about the fact that I was going to pick that up somewhere along the line. I just caught it. Okay, so this could be positive or negative. Sorry, that is totally my bad. So here, let's go back and test it again. So if I put -3 in here, again, this is always going to be negative up top. -3 squared is 9, -4 is positive, cube of positive, I get positive, so it's negative over positive, negative. Okay, then we go to -1. Numerator is always negative, but now I plug -1 in here. -1 squared is 1, 1 minus 4 is negative, a negative cubed is negative, so negative over negative is positive. Right, I do the same thing for 0. Again, numerator is going to be negative. 0 minus 4 is negative. Cubed is negative. Negative divided by negative is positive. And then I put in 1 here. Again, negative. And then 1 squared is 1 minus 4 is negative. Cubed is negative. So negative divided by negative is positive. This is going to be undefined here. All right, and then we put in 3. All right, so all negative. 3 squared is 9, minus 4 is 5. Positive, cubed is positive, so negative divided by positive is negative. Phew. Sorry, I let that go for so long. Okay, so then let's write the characteristics of the graph. All right, so the things that we want to say are whether it's increasing or decreasing. That's what this column is going to be. And this is going to tell us whether it's concave up or concave down. All right, so when it's negative here in the first derivative, what does that mean? All right, that means it's decreasing. And then when it's negative here, right, that means concave down. All right, here negative means it's decreasing, and here it's concave up. Right, this again gives us a potential critical number. So we have to be on the lookout as we're making our interpretation. So we want to see, does it, again, if this is truly a max or a min, then when we look in here, it has to go from either increasing to decreasing or decreasing to increasing. And we see that it does. It goes from decreasing, then it's 0, then it's increasing. So this truly is a max or a min. We just have to decide which. All right, so again, hopefully you remember that as it goes from decreasing to increasing, it is a relative min. This would also be an opportunity for us to use the second derivative test. Again, we said we don't really know what the point of it is because it seems like it's extra work to take the second derivative, but we could note here, hey, this is a critical number and it is positive here. Again, if it's positive there, it means it's concave up, which means that point must be a relative min. That would be another way to make that conclusion right there. Okay, here we're going to say this is increasing because it's positive and it's concave up. And then here we're going to say it's increasing, but it's concave down. All right, so let's graph this. So let's put on our vertical asymptotes. We're at -2 and at +2. Again, we're going to have to go back and take some of our information from the previous page. We just did those. We've got x-intercepts at positive and -3. So let me put them on there, positive and -3. Again, that's the symmetry part of it. We're going to have a y-intercept of 4.5, 9/2. So we'll have that up here. And I believe that's it. Then the only other points we have to put on here is, well, it's already on here, 0, 9/2. That was our critical number. We don't always get a critical number being one that we already have because, say, it's the x or y intercept. So sometimes it might be a legit point that we could put on here. Also, we note that we have a horizontal asymptote at y equals 2. That's the final thing that we have. Okay, so then we can say, well, from -infinity to -2, it is decreasing and concave down. And then from negative, well, let's see that, yeah. So we're going to say, well, we've got to have it concave down and decreasing. And again, we also know it's got to approach that vertical asymptote, so it's got to look something like this. Sorry, my graphs are probably not going to show up super well because this graph is really dark, or the grid is really dark. All right, so that's got to be there. All right, then from -2 to 0, it's decreasing but concave up. All right, well, I've got to be decreasing but concave up. That means it's got to look like this. We also know at 0 it's a relative min, and so our tangent line has to be horizontal there. All right, from 0 to 2, it's now increasing and concave up. Well, that would look like this. And then finally, from 2 to infinity, it's increasing but concave down. All right, so increasing is going to rise as we go from left to right, but it's got to be concave down, which would look like that. All right, so there is what our graph looks like. Again, these might not be the exact points right there. Maybe it crosses over line y equals 1 at, this point right here and not this one right here, but we're just looking for a general sketch. Okay, we'll take a look at example 2.